Hi there, there's another lesson for us on exercise 5b, which is a further maths topic for year 12 maths. And what we're looking at today is what happens when you get complex roots to equations, cubic equations, quadratic equations, in generally they're called polynomial equations. We actually have one here which is a polynomial, it's a cubic. You can tell it's a cubic because of the shape of it, I suppose, and also it seems to cross in three places, which what you expect cubics to do, they don't always do. And it seems it crosses in -4, -1 and 2, and it's described at the bottom as 3 real roots. We don't always get real roots, sometimes you get what are called complex roots, and this happens actually when it doesn't cross at all. So this might be -4 again, but you'll notice it goes up, and it doesn't quite go low enough before it turns up again. This would give me complex roots. So look out for these examples where we get complex roots, and let's have a look at this then. Now this is basically the key rule for us. The key rule is that when you have what are called real polynomials, and I'll talk about what a real polynomial is in a bit, but when you have a real polynomial which has a complex root, that complex root comes with another friend, as it were. So if I get a root which says z equals 3 plus 2i, I know straight away I get another one, and that is z star, which we know the complex conjugate is 3 minus 2i, and these always come in pairs. So whenever you get 1, you get 2. And this is very, very useful rule. Notice it's written here, so if the function with z going into it gives me 0, then put z star into it, it will also give me 0. Now I haven't said what a real polynomial is. This result is not true, it says here, if the polynomial has complex coefficients. So if we get a complex coefficient such as this one, and this equation says f of z equals z squared plus iz, it's often easy to mistake z's with 2's, plus iz plus 2, in fact it doesn't say plus, it says minus. Now they are saying there's two solutions. One is z is minus I, and the other one is 2i, z is 2i. Notice these aren't complex conjugates. They're not complex conjugates because it wasn't a real polynomial. This is the problem. This here, it says minus iz. If it said minus 2z, no problem, because it's a complex number there. Therefore we get a problem. Notice, by the way, very often these are written f of z equals, and you'll get some kind of expression in z. Very often they're written x. The z's a bit of a clue, because if it says z, it's telling you to expect complex roots. If it says f of x, it might be either. So I suppose if they're cruel to you, they'll write f of x, and you'll have to spot that it's got complex roots. If they're nice to you, they'll write f of z, and you'll know you're expecting to find complex roots. So that's the subtle difference between when you get the equation written in z's or x's. So I've got an equation here. Now notice I've done it in x's. It says we've got a quadratic equation with real coefficients. This is the type we want, of course. X squared plus bx plus c. So I know b and c must be real. And it has one root at 5 plus 2i, and find the values of b and c in the original equation. But notice, as soon as I get one root, therefore I've got another one as well. So I've got that root and I've got this root as my two z's. If like z equals, which one was it? This one was z, and this one here is my z star. Now I think I need just to remind you what you do normally. Say you had x squared minus 5x plus 6 equals 0, and it was all a nice one. When you factorize it, you might even spot on your calculator or in your head that your answers are x equals 3 and x equals 2. Now from that, you might realize what the factorized version is. You might, well, you should remember you always had to change the sign to go from here to here. So going backwards, you have to change it as well. It's x minus that root, and it's x minus that 2 as well, equal to 0. And so this is really what we've got here. We've got these solutions, and we've kind of got to go backwards to get our factorized form. And so I suppose if I was doing this properly, I'd write x minus this thing, need double bracket, and x minus the other one. What was it? Minus 5 minus 2i. Now it's not very nice, is it? But this is a little rule down here. This is why I've written it down here. If you ever do x minus z times by x minus z star, which is effectively what I've got here, you'll notice it's x squared minus 2 times the real parts of the z. Now the real parts of the z here is the 5. The real part of the z equals 5. And the imaginary part's this too. But notice, effectively, when you multiply them out, the imaginary parts will disappear. Try it if you don't believe it. But it's a bit messy. So I'm just going to write this is equal to x squared minus, it says two lots of the real, so I'm going to say minus 10x. And it says plus the magnitude of the z squared. Now to get the magnitude of the z squared, you just do 5 squared plus 2 squared. And that's 29. Now notice I've said square it, and that's why I've not bothered with the square root. Normally you'd square root it. But if you want it, z squared, that's what it is, equal to 0. Because it was equal to 0 at the top. So what have I got? Minus 10 and 29, yes, that's what I've got. Let's do another example. This time it's a cubic example. It says x cubed plus x squared plus x plus 21 equals 0, has a root that. And because it says this is an equation with real coefficients, which I can see, there's no dodgy i's and stuff in there. My first solution is z1 minus root 6i. There it is. But then I also know that z star is 1 plus root 6i. It says factorize the polynomial. Now, in order to factorize the polynomial, one thing I'm going to have to do is multiply these out, a bit like I just did, using this trick down here again. So I'll do x minus it. So x minus 1 minus root 6i, put that in the bracket. And I'm going to times that by x minus 1 plus root 6i. Put it in the bracket. And when I multiply it out, I will know I'll get x squared. Minus 2 times the real part. What's the real part? The real part is just 1, so minus 2x. And when I come to do the magnitude of z, I'll square the 1, which will be 1 squared, which is 1. I'll square the root 6, which is 6. So it equals 7. So if you like, that's really what I've done. The magnitude of z squared is 7. So I can just write plus 7. Now, is that the answer? Clearly not. My answer is a cubic, and I've only got a quadratic. And that's because I've got another thing still to do here, and what I'm going to do is just show you how to find the last part of this. So I've got x squared minus 2x plus 7, and I want to know how many times that goes into my initial expression. My initial expression was x cubed plus x squared plus x plus 21. And if I divide this into this and work out what I multiply this by to get my final answer, then I will get my third root. So x squared times by x gives me x cubed. X times by minus 2x gives me minus 2x squared. Notice I've got to do this 3 times. X times by 7 is plus, it's plus 7x. I was going wrong there. Going mad at least. So take them away. X cubed, take away x cubed is nothing. X squared minus a minus 2x squared. I reckon that's 3x squared. And then x minus 7. I reckon that's minus 6x plus 21. Now you can see, that's lucky. Look, when I times x squared by 3, now back multiply, I get 3x squared minus 6x plus 21, and when I take one away from the other, I will get nothing. So this tells me this is how many times it goes in, and therefore my factorized version of this, f of x, is equal to x plus 3. I suppose it's technically I need to write this bit down here. So it's x squared minus 2x plus 7. I nearly wrote it in its complex root form, but you can't really write it like that. It's such a mess. So I'm going to say that's my factorized form. And what it says, write down all the roots. So well, we've got 3 roots, haven't we? The 3 roots are, well, they told me one. It was 1 minus root 6i. I knew straight away it was 1 plus root 6i. And I just found out from my bracket here, x plus 3, just found out that minus 3 is also a root. Notice I changed the sign again. And that's what I've got. Good. Another, well, it looks very similar, doesn't it? We've got another cubic equation with real coefficients. This says it's a backward equation. This is almost like that first one I did, I think. Now straight away I've got a root at 3. So I've got z equals 3 as 1. I've got z equals 4 plus I. That's a complex one, so I immediately get another one, z star It's 4 minus I. So I can write it out. Well, I kind of can. I'm just going to say this gives me a little way to write out the two of them. So dealing just with these two initially, I've got f of x is equal to, well, we've got something at the start. Let's not write that. I'm just going to write them out. It's x minus the 4 plus I. And it's x minus the 4 minus I. And as we've saw down here, we have to double this 4 and take it away. So it's going to be x squared minus 8x. And I need to find that magnitude squared again. And that was 4 squared is 16. That gives me 1 squared, which is 1. I reckon 17. So it's plus 17. Now this is the reason why I crossed out the f of x here, because now I can write f of x. F of x equals, well, I've got this 3 here for my first root. So that's x minus 3 times by x squared minus 8x plus 17. Does it want? Yes, it wants me to multiply it out now, doesn't it? What's that gives me? It gives me x cubed. That's easy enough. Minus 8x plus 8x squared, that plus 17x minus 3x squared plus 24x minus 51. And so when I simplify this, I get x cubed. Those two give me minus 11x squared, according to me anyway, plus 41x minus 51. No idea if that's right. Certainly looks right. Good. And I think I might have time just to show you this last example. We've got a real polynomial equation again. Notice this one, it's badly done. It should have said f of z. But it's written in z, and that tells me I've got some complex numbers coming my way. And it's, in fact, it's got two. It's got 3i and 5 minus i. Notice this is a real polynomial equation, but it is a quartic. We've not seen a quartic example before. So we've got z equal to 3i. Notice we've immediately got z star equal to minus 3i. Notice I just changed the sign of the i's. There was no real part. And we've also got z equals 5 minus I. So we've also got z star equal to 5 plus I. I think I'm going to have to do my little trick for both of them. So for the first one, I'm going to get z squared. Now it does say the real part you double, and there's no real part, so there's no z in the middle of this expression. And I suppose this is a bit confusing because it says x's and here it says z, but I'm going to just play along with it. And I just got to find the magnitude. I reckon the magnitude of that is 9. So it says plus 9 when I do that. So that's my first expression. When I do this one, it will be z squared, double the 5, so minus 10z. And now I find the squared, and it will be 25 plus 1, I reckon 26. So this is plus 26, and that's my second expression. And, of course, it's a bit confusing because it's z's, not x's, but other than that, it's the same. I reckon my f of z is that first one, z squared plus 9, which is what I get when I do these two roots times by each other. And then I did these two roots times by each other, which is now z squared minus 10z plus 26. And I think if I multiply these out, I'll get my overall expression. So let's see what I get. I get z to the 4 minus 10z cubed plus 26z squared. Easy to get the powers wrong on these, isn't it? Plus 9z squared minus 90z. 26 times 9, 234 plus 234. So that's z to the 4 minus 10z cubed, plus, we can add those together, plus 35z squared minus 90z plus 234. It's relatively easy to simplify because there's only one term that sort of doubled up this z squared. So the roots are those which we agreed with, and my final expression is that. I think that's right. So look, we're going to practice a couple more of these, and then I'll set you going on these examples from the textbook, which is exercise 5b. And this, by the way, is an alternative way of writing it. It's interesting I've done that there. Best luck.